We're now going to talk about how airfoil geometry is defined. And remember that an airfoil is just the cross-sectional cut through a wing. So if we were to take this wing and do a cut at some span-wise coordinate and look at the geometry, that's what we call an airfoil. And a lot of times they look something like this, kind of a teardrop type of shape, and they come back to a point. And I'm actually going to draw that a little bit exaggerated so we can talk about how that airfoil is actually defined. So we're going to draw it something like this. And there's a couple important geometric characteristics or the way that we define this airfoil. First of all, it's got a leading edge and a trailing edge. And the leading edge isn't necessarily the furthest point forward on the airfoil. But what it is, it's the beginning of what's called the camber line. And the camber line is a line that is midway between the upper surface and the lower surface. And usually has some shape kind of like that to it. Okay, so let's define a few things here. So we've got the leading edge here at the front, and the length here between the leading edge and the trailing edge is called the chord. That's the chord length of the airfoil. And we generally then draw a coordinate system along the chord and say that that's X and Y. And then we're going to have some function that defines this camber line. The camber line is going to be some function of X. So I'll just put that over here. Camber equals some function of X, where you put in X along the chord and it returns the Y, and we actually usually call that Y camber of X. Okay, then the airfoil also has a thickness, which we call T of X. The thickness varies as a function of X, and that thickness is then used perpendicular to the local camber line in order to define the upper and lower surfaces. So at any point X, we come up to our YC of X over here, our camber point, and then we're going to go perpendicular to that by a thickness, by the T of X. So this is a T of X here, and this is YC of X in here. So the height there is YC up to the camber line, and then the thickness is measured perpendicular. I'll just make that's perpendicular to the local camber line. And then that thickness then is used to figure out where the points on the upper and lower surface are. Okay, so let's talk about where those points are, and I guess really quickly I'll just finish labeling a couple things here. So this is called the leading edge, and this point back here is called the trailing edge. And notice, because the camber line can have some slope up at the leading edge and some thickness, well, the thickness goes to 0 right at the leading edge, but then shortly after that it can have some thickness. The airfoil can actually extend out in the X direction a little bit further than the leading edge. So the leading edge is not necessarily the furthest forward point on the airfoil, because the camber line is generally making some, coming off at some angle to that, and the thickness is measured perpendicular to that. So it's not uncommon for some of the airfoil to extend forward of the technical leading edge of the airfoil. And sometimes people get those points kind of mixed up or interchanged. Some will call the leading edge of the airfoil that forwardmost point, but technically it's the beginning point of the camber line that defines this airfoil. That's technically the leading edge, and then the trailing edge is really difficult to confuse because usually the airfoil comes back to something close to a point. Some airfoils actually have a finite thickness back here, but they're very small compared to the rest of the geometry of the airfoil generally. Okay, so let's write an equation now. We can actually find where the upper x location is. So the upper x location is my x coordinate minus 1/2 of the thickness at that x coordinate times the sine of theta, where theta is this angle here. That's the angle that my camber line makes with the horizontal or with the x-axis. So it's basically the slope of the camber line. Okay, so if we know the slope of the camber line at some point, and we know the thickness, we know the theta, and we know the thickness, then the upper location is just my local x, whatever I put in for x there, minus 1/2 of the thickness times the sine of theta. Okay, so that's how I get from this point up to that point. Okay, so let's look at the y upper, and that's going to be my camber line location at x plus 1/2 of the local thickness times the cosine of theta. And then we can do the same for the lower. So we have our x lower location is going to be x plus 1/2 my local thickness. Oops, let me fix that. My local thickness times the sine of theta, and my y lower is y camber at that x location minus 1/2 my local thickness times the cosine of theta. Okay, so this basically, these are this is how the upper and lower surfaces of that airfoil are defined, and I'll just put, so we've got our x upper, y upper right there, and then our lower here, this is going to be x lower and y lower. That's that point right there. Now, in many textbooks, this is the way that they define the upper and lower surfaces. I've seen it, though, where that's taken one step further, I guess you could say, because we can say that the tangent of theta is equal to the change in yc with respect to x. So it's the slope of our line up there, our theta angle is related to the change in our camber line with respect to x. It's basically the local slope of that line is equal to the tangent of theta. And so you can use this, we can use a trigonometric identity to get rid of these sines and cosines and instead put everything in terms of the camber line slope. And that can be useful in some scenarios. And so another way to write this whole set of locations is that the x upper would be x minus, and I'm going to just use a capital K here for some constant. And it's actually not a constant, it's a function of x. Let me put that in there. So K of x. And once we use this trigonometric identity, that's equal to t of x over 2 times the square root of 1 plus dyc dx squared. So that is all underneath the the square root, and then we've got a 2 out front. Okay, anyway, so this is that k of x, I'm calling it. So that x upper is x minus k of x times dyc dx, so the local slope. Y upper is equal to the camber line at x plus k of x. And then we've got the x lower, which is equal to x plus k of x, again times dyc dx. And y lower is just the yc of x minus k of x. Okay, so this is just another way to express it. What it allows us to do is get rid of the sines and cosines and express it just in terms of the local slope of the camber line. Okay, so these are two equivalent ways of expressing the upper and lower surfaces. I've seen both in different textbooks, and but they're two different equivalent ways of expressing that. Now, one more thing I want to point out about airfoils is that most of the time at the leading edge here, see, the airfoil is going to have some curvature because we've got some thickness as a function of x, and the thickness goes to 0 at the leading edge and at the trailing edge, but generally the thickness is more forward here on the airfoil, and as we go back to the back, it tapers off and comes down to a point. So, but up at the front, we can actually look at the curvature of this airfoil, and right at the leading edge, that curvature has to go to some constant value, and because you have an upper surface and a lower surface coming together, and you don't want to have a discontinuity in the curvature of that airfoil. So the way that we do that is the leading edge there is basically it's basically defined by the radius of some circle that would have a tangent. The edge of that circle would be tangent there along the leading edge. And so because of that, most T of x functions, most thickness functions, start off with some constant. I'll just write this down here. So most of them start off with some constant, I'll just call it a for now, times the square root of x over c. And a lot of times we put this x over c, that's just a percent chord. It goes from 0 to 1 as you move from the leading edge to the trailing edge. But anyway, a lot of times we start off with something like that, and then it'll be plus some other terms here that then define the rest of the thickness. But as x goes to 0, this front term dominates. So the rest of these terms go to 0 as x goes to 0. But the leading term here dominates as x goes to 0 and approaches a circle with some radius or some curvature that's defined or related to this constant out front. So there are different many different thickness distributions out there that can be used for an airfoil, but most of the time we see something like this where we start off with some square root of x over c as this leading dominant term as x goes to 0 of the thickness. And then obviously as you move away from 0, then these other terms here dominate and fill out the thickness distribution.